Hello, welcome back to the continuing lecture series in investments. Now, so in our last session, we talked about basically, the how to combine a risky portfolio, right? Using by allocating weight, given weight in this case, over stock portfolio and bond portfolio, right? And we calculated expected return and standard deviation of the risky portfolio. Now, because the scenario analysis it has limitations. In other words, the scenario analysis is of normal distribution, right? Because the assumption started from, in most cases they would use, a more sophisticated, scenario than just, 4 cases, right? Or 4 discrete cases, right? As I said, how would you, what makes you so sure that the severe, of course, it's it's at the discretion of the analyst, right, or the fund manager to put 5%, bottom 5% as the worst case scenario. But even under that kind of scenario, right, the return, the probability for that probability, giving those discrete segments, right, like probability segments, that is kind of too simplified. And as I said, those probabilities are basically, all continuous, right? It's on a continuum. So more, and the returns are pretty much, based on the past data, or to emulate the normal distribution, they should use Monte Carlo simulation, Monte Carlo studies. But again, that's basically, if you use the fund manager's discretion to his own judgment to based on his experience and gut feeling, right? That's not science, right? That's not science, really. But anyway, the idea is that a lot of actual fund managers, they rely on the gut feeling and their experience. But anyway, the idea is, the point is, instead of that kind of predetermined scenarios, it would be more seamless and realistic, or it would more reflect the normal distribution if you use historical data. Of course, historical data, time series, right? So, and if you use historical data, we have plenty of data points to calculate, mean and variance, and but here also there is some downside to historical data, because you cannot estimate averages as precisely from past returns. In other words, expected return is always expected return. Never, ever. I mean, there may be a chance. The mean of the past return is not exactly what's going to happen in the future, right? That's what I'm saying. I mean, and the expected return, the mean, you've got from the past returns, is not a value that has ever happened in the past. Okay, this is not a. I'm not saying 100% of the times this is the case. Excuse me. But almost, the mean doesn't have to be. I mean, it can happen. One of the in the past, by some happenstance, right, by pure luck, by pure chance, uh, the mean return may have maybe one of the numbers that have happened, but almost 99% of the time, it's really rare. The average is not what has happened in the past. It's just, but anyway, averages of past returns provide highly noisy forecast of expected returns. And what's going to happen, actually realized return in the future may not, most of the times, may not be exactly the expected return. But, that's fine. I mean, expected return as a, it's, a strong basis for, rational basis or, strong, reasoning that supports, why it is, expected return. So we focus, our focus for risk is more on deviations of returns from average value, right? For taking, average return from the mean return from the past data is for calculating the deviations, or standard deviation, variance and standard deviation. And also correlation, this is between stocks and bonds, right? A realistic correlation between stocks and bonds based on historical experience is actually about slightly positive, right? Slightly positive. 0.2, right? Slightly positive. So, and why we need, why do we need, we calculated correlation last time, right? We calculated correlation. Why do we need correlation? Again, covariance is part of, covariance. Covariance is, includes covariance, includes, correlation, right? I mean, it's covariance, it's common variance between the two random variable x and y. So correlation between the two is, an integral part or, essential element of the covariance. And this is, basically, covariance of x and y. Covariance of x. In this case, it's S and B, stock and bond. Yeah. It's so tricky. Now, so now let's think about it. We know how to find return. Return is weighted average, right? So weight of bond times return on the bond, return on the risky portfolio, right? A weight of stock times return on the stocks. If it is expected return on the portfolio, weight of bond and expected return on the bond. In other words, the mean return from the past data, weight of stock, mean return from the past data. The variance, this is how we find the variance, right? Of the risky portfolio. Why? Now, I just have to remind you, recall your memory, jostle your memory of FNB 100. And if you took FNB 100 with me, at least you would remember this. Let me go back to, okay, I'll have to stop sharing this and let me share. This file, and you should be seeing it about now. Yeah. So this is actually, the material from Finance 100. In Finance 100, I showed you why the variance of the portfolio with two assets, or two random variables, x and y, are random variables. Asset x is, let's say, stock, and asset y would be, a bond, and there is no, some correlation between the two, but they are basically independently moving, right? These two variables are both independently moving. So then, how would you calculate the so it's basically the variance of the portfolio is basically the weighted average of the standard deviation, right? Weighted average of standard deviation squared. Okay. So then, if you recall the expansion rule, right? From this is like very basic algebra, right? Factorization and expansion. Like x plus y squared. This is like 8th grade math. X plus y squared is x squared plus 2xy plus y squared, right? But if x and y are random variables, correlated with each other, the formula becomes, there's a correlation, right? You have to enter correlation between the two. You have to factor that in, and then the correlation is basically, between x and y is covariance over standard deviation of x times standard deviation of y. And then that makes covariance rho times this, correlation times this. Okay. And then if you expand it, then it's weight of x and times standard deviation of x squared. I mean, you don't have to square it one by one. I mean, multiply these two and square. That works. Okay. And then this is then 2 times weight of x, weight of y, standard deviation of x and y, times correlation between x and y, which can be captured by covariance, simply by covariance, plus weight of y times standard deviation of y squared, right? It's basically variance of y. So suppose and as an extreme example, I assumed the correlation of -1. If x and y are perfectly negatively correlated, and what's the variance going to be? And then if you work out those numbers, the variance will completely cancel out, right? They cancel out each other. Variance becomes 0. That means if you can construct a portfolio, if you can find 2 assets that are negatively correlated, perfectly negatively correlated, and which means correlation coefficient of -1, and the risk is completely diversified away. That means the risk is completely diversified away, 0 risk, right? So that is basically the idea behind it. So let me go back to so I gotta stop this and back to our PowerPoint. Okay, you should be seeing it about now. Yeah, you should see it about now. So and our goal is, of course, basically, our goal is then we want to find the optimal weight that would minimize this variance, right? Our goal is to okay. We may not be able to completely offset or cancel out the variance, but we want to find that optimal weight that will minimize our variance. Okay, minimizing our variance. Come on. So if we can find that weight, wouldn't it be wonderful? Then it will minimize our variance, right? So if that weight is based on the bond, then the weight on the stock is simply 1 minus weight on the bond. Make sense? And how do you find that weight? This is the formula. It's a very arduous job, I derived the formula. I mean, the textbooks just give you the result, they don't show you the process. They just throw this at you. And I'm not the kind of person who can just live with it. I have to actually uh, derive the result. I have to see the process myself. I have to. So I actually cracked. When I was a uh, uh, doctoral student, I labored over it, and actually, it's basically, if you are in economics, it's economics is all about, optimization. This microeconomics, especially microeconomics, is all about optimization. All you learn in microeconomics is how to maximize profit, how to minimize cost, optimization, maximization, or minimization. It's all calculus. It's all calculus. So what do we want to minimize? We want to minimize the variance. Okay, so this is the variance. And then we want to uh, take the first derivative of the variance with respect to weight, right? With respect to the weight of the bond, right? So in other words, then we take the first, derivative, and through that process, and that's a kind of, mechanical but arduous process to actually, bring it down to a very convenient form to. And of course, the first order condition, second order condition in economics is basically, that's also in math, in calculus, first order condition is to find that inflection point, and at the inflection point, the slope is always zero. Now, isn't this taking the slope? If you're with respect to weight, so set it equal to zero, and then solving it for rearranging it, solving it for weight of the bond, then I arrived at this. So this is, basically, how they came up with this formula, right? Okay. So we're not gonna we're gonna come back to this later. Risk return trade-off, mean variance criterion. This is quite obvious. So we're gonna go straight to this example, and how did they generate this? I mean, what is this about? This is, basically under these weights. I mean, they tried out all, weights, trying to find the minimum variance weight, right? Minimum variance portfolio weight. In other words, the weight of bond and stocks that would minimize the variance of the risky portfolio. So to do that, actually, I'm gonna have to switch and then bring up the Excel. Okay, you should be able to see it just about now. Okay, there you go. So here, it looks quite complicated. I've already found, minimum weight. I have already found now using, but let's replicate what they did in the. First of all, these are given parameters, right? They gave, 15% is the stock portfolio return, expected return. 9% is the bond portfolio expected return. And the variance, standard deviations, they're all given. I didn't have to, bond 23%. For a bond portfolio to have 23%, standard deviation, that is a very risky bond portfolio, isn't it right? It's almost two-thirds of the stocks variation. Correlation is given, right? So under these given scenarios, right? And I calculated covariance is basically what? Standard deviation of X, standard deviation of Y, and correlation between X and Y. That's covariance, right? So why do I need that? because I'm going to have to find the variance, right? I have already found the expected return here. I'm going to delete all of them. Now, and I found the optimal weight in the bond. I mean, minimum, right? Minimum. Uh, in other words, that's the weight that makes the variance minimum. So basically, using rule, right? Using that formula. That formula is, so complicated, right? Um, but if you diligently and dutifully, it's very. I like people who are very beautiful. Not beautiful. I mean, I like beautiful people as well. But beautiful people who have strong sense of duties. They never fail. They live up to their duties, or sometimes even more. It's not just doing their duties. It becomes a passion. I mean, being there. If you work, if you have to report to work at 9 o'clock, uh, arriving by 9 o'clock is not enough because you may be able to punch in your time card at 9 o'clock, but you're not safe. What if it's always better to, it's too tight, isn't it right? If you just arrive at 9 o'clock, everything is too tight. So give yourself some room, right, to be on the safe side. Then when do you leave home, I mean, if it takes 1 hour to get to work, you don't leave, 1 hour before work or class. You leave, with some, slack. Like, you leave, 1 hour, 10 minutes before, 1 hour, 15 minutes before. Then you arrive at work with some slack, with some room, right? Um, you arrive at work 10 to 15 minutes or class 10 to 15 minutes earlier, then this is the time you can reflect. You can use, to reflect, and you get better. You're more tuned uh, to work or to your class. That makes you perform better. I mean, if this becomes, like your religious habit, then you get ahead. You get ahead of other people. You're getting ahead, and it takes up just one small step. Not just being, dutiful, but um, you know, uh, uh, you do more than just, uh, the boundaries of the duty, right? And it becomes a habit, and because from that habit you get more uh, reward, right? You get more output from just putting that extra input. So you take pleasure in it. You like, it becomes, although it's a small pleasure, it becomes, pleasurable to uh, get there a little bit early, and uh, it becomes, it may not be, passion, but you become eager and enthusiastic person, and that's what separates, winners from losers, right? So being dutiful, right? Uh, if you stick to this, dutifully, right, which takes, a lot of discipline. Duty, being dutiful takes a lot of discipline, right? If you don't have a disciplined mind, you can't, excel. So anyway, if you do it like that, and um, I found, weight, okay. Uh, so here, and then let me find the return, we know it's basically a weight. That's my phone ringing, but come on, let me get things. So it's weight times the return, and I'm gonna lock that because by hitting F4, you know why we have to lock it, right? Because I'm gonna drag it down plus the weight times the return on the bond. I'm gonna lock it, and then I'm gonna drag it down later. But after doing so the variance is of the portfolio is the weight times the standard deviation of the stock, and I'm gonna lock. And I'm gonna square product. And then times the weight of the bond times the standard deviation of the bond, and I'm gonna also lock that. And, and 2 times standard deviation of stock times standard deviation of bond times correlation between the two. But that is basically already done. That's this, right? But we need the we forgot about weight, so we're gonna do weight times of stock times of bond times this times this is already this, so I'm gonna just point to that, and also I'll have to lock it because I'm gonna drag it down. Hitting F4, I locked it. Okay, and then that's the portfolio variance, right? And then portfolio standard deviation is simply the square root of variance. Enter. Now, the minute I did that, a plot appears because I already built it, because this plot will emulate this plot will basically graph the variance and the standard deviation and the return. So I'm gonna copy and drag it down. Then I'm gonna also a bit. And this one is already found this already previously, and so that's why there was a dot there before, and I'm gonna copy that. Why? Because this is the weight is the. But let me do this first. And these cells, I'm gonna drag it down all the way. Okay, and and I should have probably okay. this was done separately because, as you can see, it is the weight was already found, here using the this formula, right? And you might think, and I will tell you, I will show this formula looks different from this. Yes, it is different because it is to find optimal weight, not the optimal weight is what? I mean, aren't we finding the weight that minimizes the variance? Yes, it minimizes the variance, but minimum variance isn't always give minimum variance doesn't always give you the highest return, right? So what is the point? The point is minimum variance weight is important in its own, but if the return is not the maximum for that variance, right? That's not the optimal weight. Optimal weight is what? What optimal weight is? The weight that gives you the highest return for a given risk. So in other words, optimal weight will have to give you the highest Sharpe ratio. So optimal weight is the Sharpe ratio maximizing weight distribution, right? So that was separately calculated. But let me anyway try, because the whole thing, because the graph isn't smooth because of. But let me continue. Well, anyway, it's the same thing. It is the same thing, right? But you might wonder, it is it doesn't look like continuous curve. Why is it, suddenly there's something like, well, it's because, look, this minimum variance is not, it's found, I mean, first we had, variance that is in the order of 765, and then without 4, suddenly 3, right? And then 4, and then 3, and then 4, and 5. So roughly, it would have this curve. It would show this curvature, but it isn't, like a seamlessly continuous curvature. Okay. Well, I gotta. So if we are at this point, I'm gonna have to stop recording because we've over, overrun our time. Alrighty, that's it for now. I'm gonna see you guys in the next video. Stop recording.